So last time we saw that we can give an operational meaning in terms of statistical distance to the distance between two quantum states, and that the distance between two quantum states psi1 and psi2 can be defined in this way, where f is called the fidelity, is just the absolute value of the overlap between two states. And we defined the differential version of this distance that is called the Fubini-Studi metric, which is just this that you obtain by expanding cosine to the minus 1. Okay. So when you have two states that are whose overlap is very close to 1, their statistical distance can be written in this way. So today we want to understand how these definitions that are interesting from the point of view of the interpretation, the foundations of quantum mechanics, but how do they help us in defining some more precise criterion for quantum phase transitions? So now we are not concerned to any states, any two states in the Hilbert space, but quantum states that are ground states of Hamiltonians that are of physical interest. Okay? And we want to see how we can define a phase with this. Okay, so as we said many times, our Hamiltonian is a smooth family of Hamiltonians, depending on some parameters. So mind that this n is not the dimension of the Hilbert space. Okay? Like in the Ising model, you have one parameter, so n is 1, but you have a many-body Hamiltonian. So this is just the dimension of the parameter space. So today we'll see something in how this plays a role. So here we have three types of dimensions. So just to, we have, okay, so let me call this, let me choose another P. Okay. We have the Hilbert space, if it is something like this, means that n is the dimension of the Hilbert space. Then we have P, that is the dimension of our parameter space that I will call M. And finally, we have D, that is the real space dimension. All these things we'll see play a role. So by the way, because we introduce all our relationships in a graph theoretic way without embedding our system in a space, in R3 or something else, how do we know what is D in a graph? So if I give you a graph.
So, excuse me, M is the dimension of the Hilbert space, and
P is the dimension of M. Oh, looks like H. M is the parameter space. So it's this manifold of parameters. We have a lambda living here, and we will make lambda live on a curve. Okay? So this is lambda of S. And then you have the parametric equation of the curve, right? Okay. And what do we do with this? For every lambda, we have a Hamiltonian, and so for every point here, we have the ground state of the Hamiltonian. For sake of simplicity, we will consider the case in which the ground state is unique. There is no loss of generality in what we are here. The generality is not very important. Okay, so if I so you know that this graph must be 2D, right? Because I drew it on the blackboard, right? But so in general, if I just give you, by the way, so you remember how we define a graph, right? We have a set, and then we say what are the edges of this set. So every graph, at least when graphs in which the edges are links, so just links between 2 points, can be written as a matrix called the adjacency matrix. And you simply, here you label the points in the graph, okay? And you put at 0 if there is no link between 2 points, and the 1 if there is a link between 2 points. So this is undirected, means there is no direction in the links. And if we don't consider the case in which there can be loops like this, then you would have always 0 on the diagonal, then it's symmetric, and you have some matrix in which, you have some ones wherever there are links. So if I give you this is the object that mathematically represents the graph. If I give you this, can you read out the dimension from this? Or we need some additional structure to define a dimension? What do you think? What does your intuition tell you?
You can do like a random walk on like a certain point and see how it diffuses. But
that's a good idea. That's a very good idea. And in fact, the real answer has a lot to do with what you're saying. But it's a bit simpler than your idea. But the two things are related. Okay, so what you can do, okay. So let's do a simple case. When I write a chain like this, why do you really think that the only reason why I know that this is 1D is because I actually drew it on the blackboard? Or you can see something that makes it 1D. No, it's not about the degree, because, for instance, here, this is a 2D thing. It has the degrees are 4, but I can have a honeycomb lattice, right? Which each node has 3. It's still 2D. So the degree doesn't play any role. But good idea. However, not. So we do have a notion of distance, right? The distance is well defined. And we have a notion of volume. Volume is well defined. So if I ask you at a large distance, how does the number of points, so the volume, inside a ball of radius d, how does it scale? So the volume goes like L to 1, right? And I said that the dimension is 1. Here, the number of points goes like L to 2, right? This is L. So I said the dimension is 2. So in general, if the volume scales like L to the D, then I said the dimension is D. Not always this is true. There are graphs such that there is no such scaling behavior, and then you cannot define any dimension. But if you can define a dimension, so the most general thing that you can do is this. This is called Hausdorff dimension. And in fact, this is the only way in which you can define dimensions for fractals. You just see how the number of points scales with the linear sides of the system. All right, so this small d is real space dimension is defined this way. All right, so, okay, so now for our cases, these guys here is a family, depending on the parameter lambdas, of ground states of this family of Hamiltonians. Also remember that our family of Hamiltonians later will play a role, that this object is, the Hamiltonian is a local Hamiltonian. Yep?
What is the importance of the Hofstra dimension? Like in cases like space-time dimension as a degree of freedom we can go, we determine the number of basis factors to describe the point in configuration space. But what can we do with the Hofstra dimension in practical?
Well, yeah, so in practical applications, so there are two main reasons. One is fractals. Okay, so if you have a fractal object, you must use the Hausdorff dimension. You cannot. There is no other way of defining fractal dimension. But for our goals, now in this course we will not be considering fractals. Maybe we'll mention something at the end. But the reason is that I do not want to have our stuff embedded in real space. So I want the minimal number of ingredients. Why I want to do that? So we will discover it exactly next lecture. So I don't know if I need to do a detour here, but so next lecture. So one of the goals of this course is to show you how some structures can emerge in quantum many-body physics. And some are structures that are important just for condensed matter, but some others are important for physics in general. So there are points of view in which the so-called elementary particles can be seen as emergent particles from a condensed matter system. And what we will show in this course is that there are structures like Lorentz symmetry that do not need to be imposed from the beginning, as you do in quantum field theory, but that in some sense can be emergent. And we show this next time, and this result is of fundamental importance because it's interesting in itself, right? That the light cone is emergent, can be emergent, but it's also the technical tool that we need to prove our theorem on correlation functions. That is one of these big results that we want to obtain in this course. All right. Okay, so this is our guy. So we want to compute the fidelity, right? So we need to compute this overlap. So the way to do that is so for us, lambda, we pick two states on a curve that are close enough. So we will have psi 0 of corresponding as some parameter s of our curve. And you do the overlap with psi 0 at s plus ds. Okay? So it will be, so this is our fidelity f, the absolute value. This is f. So it will be, this calculation is easy, just very long. So you will do it in the tutorial tomorrow. And the result of this thing is that f can be written as 1 plus 1/2, let me write it like this, beta I, beta j, minus gamma I, gamma j, minus gamma I j, ds I, ds j. Of course, here I'm using the Einstein conventions to sum over indices, where beta I is defined like the inner product between psi and the partial derivative in the I direction of psi. By this, what I really mean is this. Okay? So I'm differentiating along the ith parameter of this curve. And gamma I, gamma j, sorry, gamma ij is equal to the real part of the inner product between the I psi, dj psi. So, and I define this object. Oh, no, okay. So this is the fidelity. Now, our Fubini study metric, which is this, 2 minus 2f. So you plug, this is f. So our Fubini study metric, well, it assumes the form of the distance in a manifold, and it is just this g mu nu, ds mu, ds nu, where g mu nu is beta I, beta j minus gamma ij. So this is called the quantum geometric tensor. It's a complex object in the sense that it's a tensor on the field of complex numbers. And gives our manifold of states a geometric structure. So because it is a complex object, we are interested in examining separately, okay, also as an object itself, but also separately the imaginary part and the real part. Okay, so this is a very straightforward calculation that you will also see in the tutorial. And so what is the precise, we call this f, I think, ij. And this is called the adiabatic curvature. So do you know what is the Berry phase? So for those who don't know, if you have a manifold of states like this, and you change lambda very slowly, adiabatically, and you do a loop, you get a phase called the Berry phase. This phase can be interpreted as what you obtain when you integrate over a connection called adiabatic connection, and the curvature associated to this connection is this guy, is the adiabatic curvature. The real part has never really been examined too much, and it is a Riemannian tensor. So the real part is positive, and it is a Riemannian tensor. And it is what it is, so one has to do the calculation. But there is a very interesting calculation, so let me show the result on the next blackboard. So so what we call capital G mu nu, which is the real part of small g mu nu, Okay, so this calculation also you will see it in tomorrow in the tutorial, but it has a very interesting expression in terms of the Hamiltonian. You see, so far, our manifold of state psi 0 of lambda is just some family of states that depends in some way from lambda. We have not used yet, until now, the fact that they are ground states, until now. But now we want to use the fact that they are ground states. So how do I use it? Well, we use perturbation theory. You see, the important ingredient is this derivative of psi, right, along your parameter. So the derivative of psi, so what is a derivative? It's like the difference between psi of lambda plus delta lambda minus psi of lambda. It is this guy, right, in the limit. But now you can compute this object in perturbation theory starting from this. And now, if this is a ground state, so what you want is the new ground state when you change your Hamiltonian of delta lambda. So if you do perturbation theory, you have this expression in terms of the Hamiltonian. So you will do this calculation tomorrow. Putting together the things, the result is this one, which is very interesting. It's the sum of n different from 0. So now this n is labeling the eigenstates of the Hamiltonian. And you have psi 0. So psi 0 depends on lambda, of course. The mu of h, also this depends on lambda. And the nth eigenstate, also this depends on lambda. And here you have, again, n. Then nu h psi 0 of lambda. And here you have the energy of the nth eigenstate minus the energy of the ground state, modulus square. So the gap with the nth eigenstate. This is a very interesting expression. And as you can see, it reminds us a little bit of the adiabatic theorem. Because here you have the gap square in the denominator. And here you have a slightly more complicated expression, but which depends, however, on the rate of change of h along the curve lambda. And you want to see if this rate of change makes you tunnel between the ground state and the first excited, and the n excited eigenstate. But you have this term twice, somehow because this is a tensor, right? So I need two indexes. I have to differentiate along the mu direction, differentiate along the nu direction. So this is a Riemannian tensor. So you can have differential geometry on the ground state manifold. Okay. So all this looks a bit formal, but now we apply it. Yep.
S is just one real number.
Because it's curved, yeah.
But, what is DSI, DSJ?
What is
DSI, DSJ? Like S.
I said it before. By DI, I mean this, where these are the parametric equation of the curve.
No, like the DSI, like the differential element.
Oh, okay, it's this. Is this.
It's d lambda. Okay.
Yeah. Okay, sorry for the abuse of notation. Yeah, sorry. Yeah, I confused S and lambda. Yes, those are d lambda I, d lambda j. Sorry.
Then how did you expand the like in the first expression, like absolute value of the inner product of phi 0?
Oh, okay, so you will do this. This is a bit long,
But is that
you will do it tomorrow.
is actually d lambda I, d lambda
Yes,
A?
correct.
It's not a ds.
So,
Yes, it's typos. Yeah.
so I and G are the same as mu and nu.
Yeah.
Yeah. Okay.
Yeah. Here Latin indexes and Greek indexes are the same because it's not pseudo-Riemannian, so it doesn't make any difference. There is no time that.
Is G mu nu, like you say, it is Riemannian tensor. But
This one,
in case of GR, like Riemann tensor has a 4 indices. So is that a like Einstein tensor or a receive tensor?
No. I said it's. I didn't say it's the Riemann tensor. I said it's a Riemannian tensor.
So,
Riemannian tensor means a tensor that is symmetric, positive, like any metric tensor. It defines a Riemannian geometry. Basically, you can do differential geometry. In fact, the metric tensor in GR is pseudo-Riemannian because it has a signature that is different, right? The signature is 1, 1, 1, minus 1. Yeah.
Is it easy to see that this thing is Riemannian or pseudo-Riemannian? Or could you make it pseudo-Riemannian?
So, okay, can you
Is it
speak
easy-
louder?
no, sorry. Is it easy to see that this metric tensor is Riemannian and not pseudo-Riemannian?
This one is Riemannian.
Yeah.
Yeah.
Because diagonal terms, or like how can you see that this thing is Riemannian?
Where do you see that? Let me think.
Oh, the diagonal terms are absolute values. Let's look at it.
As if we showed some.
Yeah, so you can show that, in fact, from the beginning, this guy is Hermitian and positive.
Hmm.
And yeah, I think it can be proven by this expression because the beta are, I think it's purely imaginary, but there is a minus psi. So the psi dip psi is purely imaginary, there is a minus psi, and this one is Riemannian, the gamma. So already this one, the G mu nu, the small G mu nu is Riemannian and positive. Okay, so let us apply these definitions to some case. So we apply it to the XY model. So I have a spin chain with n equal 2m plus 1 spins, and I have the couplings in the gamma lambda space. This is the Ising coupling in the y direction. Lambda sigma z. Okay. So you remember that the phase diagram is the following. So if this is lambda and gamma, lambda equal plus 1 is a critical line, lambda equal minus 1 is a critical one, and gamma equal 0 for lambda smaller than 1 is also a critical line. And you have diagonalized this model, and you have defined these angles theta k in terms of the epsilon k and of the Bogoliubov energy for the energy for the Bogoliubov quasiparticles, where and the ground state can be written in this way: the tensor product over all the k's of these superpositions between having no fermions at momentum k and minus k and having one fermion at the same moment. Oh, So first thing we want to do is to compute the Berry phase and see what is the, so to compute the adiabatic curvature and see what is the behavior of the adiabatic curvature when there is a quantum phase transition. So usually, the Berry phase is something that depends, scales like the surface inside the loop. Okay? So what you expect is that if you make a sequence of loops that are smaller and smaller and smaller, in the limit of this radius going to 0, your Berry phase disappears. Okay, so this is true in the, under the assumption that everything is very smooth. In particular, means that adiabatic curvature must be smooth. Now, if for some reason there is some point in which the adiabatic curvature is singular, then this limit doesn't go to 0, but goes to some finite number. Okay? So, and we'll show that if there is a quantum phase transition, it's exactly what happens, is that the adiabatic curvature diverges. So how do we do that? Well, we would like to make a loop and have a critical point inside. So however, if we do, in this phase diagram is a bit complicated, right? Because if we do it here, we get a whole piece of line inside. So it's not very clear. What we would like to do is to do a loop. We would like to have another dimension and do a loop like this around one of these lines. Okay, so we can add another dimension in our parameter space. So we can, for instance, so remember, you see lambda is the parameter here of sigma z. So it's telling me, this is a term makes you align the spins in the z direction. So if I want to do a loop around this axis, so this is the z-axis actually, the sigma z-axis. So I could rotate my all spins around z. So if I do that, so I would like to rotate, remember, in order to get a new ground state, what you have to find is the family of Hamiltonians. So we have our Hamiltonian that is a function of lambda and gamma, and we would like to rotate this Hamiltonian of an angle phi, and define in this way a new Hamiltonian that now depends on 3 parameters. And then we diagonalize it and find a new ground state, and now it's the function of all 3 parameters, and then we can do a rotation in the phi space. So what is this R phi? So we are rotating all the spins in the z direction. So to rotate one of them, we do this, right? And we rotate all of them. So we have the product of these things. The cool thing about this rotation is that this new Hamiltonian is actually diagonalizable using the same procedure. So if you redo the Jordan-Wigner transformation, the Fourier transform, and the Bogoliubov transformation, you still diagonalize it, okay? So you still can find the ground state exactly with the same method. Of course, now it has a slightly different form, which is cosine theta k over 2, 0k, 0 minus k. So this part is the same. And plus I e to the 2I phi sine theta k over 2, 1k, and 1 minus k. So all you get is this, phase. Yeah. Okay. Okay, so we want to understand what happens if we do loops that are smaller and smaller and smaller. So as you can see, if I do loops like that, the radius of this loop is gamma. Right? The radius is in the gamma space. So we want to see what happens when we compute our Berry phase and then send gamma to 0 in the thermodynamic limit. Okay, so let's see what happens. So at gamma equals 0, let me do first this consideration. Where is the other term? I think I have it. Okay. This delta k here. Okay. This small delta k, I didn't write it, is equal gamma sine k. Okay. So for gamma equals 0, delta k is 0. And therefore, large delta k is equal to the square root of epsilon square, right? So it is the modulus of epsilon. And this guy is equal to cosine of 2 pi k over n minus lambda. So you know that this equation has only a solution for real lambda only in the thermodynamic limit, right? That's why only in the thermodynamic limit the system can become gapless. Otherwise, this has no solution, so delta k is not 0. It's a positive number. So if I do my loop without a critical point inside, then this means that this is not 0, right? And therefore, cosine of theta k, which is epsilon k over delta k, is this. It will be equal to plus or minus 1 in the limit of gamma going to 0. Right? Because this is true when gamma is equal to 0. Yeah.
What's not? Oh, the coefficient.
This is epsilon k. Epsilon k is this number. Remember, it comes from the diagonalization of the xy model. Okay, so in this limit, this goes to 0, so cosine theta k is this, so it's either plus or minus 1. So this happens when there is no critical point inside the loop. Okay, because we used the fact that this guy is not 0. Okay. So let's compute the Berry phase. So in this case, so the Berry phase will be the sum of the Berry phases acquired by every spin. So I want to normalize this number, so I will compute just the average Berry phase per spin. So this will be equal to 1 over m minus I. So this is how you compute the Berry phase. You integrate between 0 and pi, and you integrate the Berry connection, that beta. So phi 0 d phi psi 0. Okay. So if you do this integral, the result is, it's a bit long, so I give you the result. The sum over all the spins, over all the momenta, of pi 1 minus cosine theta k. So you see that the result is either 0 or 2 pi, which is like 0. So it's a trivial Berry phase for gamma. This is, here I've used the fact that gamma goes to 0, right? For gamma going to 0. So which is what we expect. As we shrink our loops, our Berry phase becomes 0 or 2 pi. All right. Now let's see what happens if there is a quantum critical point.
You say there is no critical point because cosine theta k is regular and the gamma goes to
Because this guy, which is this, cannot be 0.
in any cases, even in thermodynamic limit.
Even in thermodynamic limit, it cannot be 0 because there is no solution to this equation.
But like, didn't you say that like critical? How did you define the critical point in this context? Like, did you define? You mentioned something like divergence of the.
So now our old definition, which is what we are using now to show that according to our old definition, our new definition works, is that there is, for some value of our parameters, there is a specific K0 such that in the thermodynamic limit, this energy goes to 0. So there is a quasi-particle that is gapless, that has the same energy of the ground state in the thermodynamic limit, or arbitrarily small, means then there is a bunch of other particles that have arbitrarily small energy around this. Okay? So remember, our Hamiltonian, after it's diagonalized, has this form. So it's just free fermions with the momentum k and energy delta k. So this is the energy of this quasi-particle that I call Bogoliubov quasi-particle, the quasi-particle you obtain after the Bogoliubov transformation. Okay. However, if there is a critical point, then this is 0, which immediately implies that cosine theta k is equal to 0. For that cosine theta k 0, so for that theta k 0 is equal to 0. And therefore, for every gamma, right? For that, we are considering this line. So not for every gamma, for in the limit of gamma going to 0, because we need to reach that one. Okay. So this means, so if cosine theta k is 0, where is our? So for that k, we get pi in the limit of gamma going to 0. We get the Berry phase of corresponding to k0 is equal to pi, which is non-trivial.
I'm very confused because how did you all of a sudden say cosine theta k0 is equal to 0? Are you saying that epsilon of k goes to 0?
Because so, okay, I went too fast. So cosine theta k is, what is it? It's epsilon over delta, right? delta k is this. Okay. So for k equal k0, that is the critical point, this goes to 0, and this is generally different from 0. Not depending on the value of gamma. Then I take the limit gamma equals 0 and keep and then it's still 0.
But in that you say...
So this becomes 0 to 0, but one is always 0, the other one is in the limit of gamma going to 0, so this is actually 0. Because this gamma.
So k0 is just a point such that epsilon of k is 0. Right?
Is the point such that
Epsilon k is 0.
yeah.
But
Is the point such that oh sorry, this is the small delta. The point such that delta k is 0. So both epsilon and delta become 0.
Where do we put the condition of quantum phase transition here?
This one. We want this to be 0. Okay. Okay, so we see that we get a non-trivial Berry phase. Now let's look at the real part, at the Riemannian tensor. Okay, so we have our G mu nu, and we want to compute it. So this computation also will be done in the tutorial. The main ingredient is this, is that we want to directly compute the overlap between two different values of our psi 0 as a function of our parameters lambda, where psi 0 is given by this expression. Actually, the one above, where is it? This one. This one. Okay? So psi 0 for me is that guy. That depends on gamma and lambda. Because now I don't need to use the loop around of phi around z. I just use the original Hamiltonian. Okay? So we compute the overlap. So this is in the tutorial. And there is a very
This will be actually one of the homework problems.
It's homework, okay. So in the homework, you will see that it has a very simple form that is the cosine of the product of the cosine of the difference of the two angles between the two ground states. So once you have this thing, then you can compute everything else. You can compute directly the G mu nu, because it turns out that the G mu nu is equal to 1/4 the sum over k from 1 to m of delta theta mu over delta lambda mu, the theta k, the lambda nu. Okay? So this is the result of the calculation. And so to perform this sum, we want to perform it in the thermodynamic limit, and we will use a trick. The trick is that the discrete sum of k from 1 to m becomes the integral between 0 and pi of a continuous variable x normalized by L over 2p, where, n. N is 2m plus 1. So if you do this and you compute these derivatives, what you find is that G mu nu is equal n over 16, absolute value of gamma. So this is, you need to do two results in two different domains because of the derivatives. So let me show just the one for modulus lambda smaller than 1. So you have 4 components, right? Because it's mu and nu. You get 0 here, 0 here, 1 minus lambda square to the minus 1, 1 plus gamma modulus to the minus 2. Okay, so this is the result. Now let's try to interpret it. So this is our metric tensor. So first of all, it depends on n. You see, the distances become larger and larger just with the number of spins. So you remember when we discussed this thing that, you know, the overlap between any two states has to scale with n because of the orthogonality catastrophe. In the differential form, this shows up here. So this is normal. This is not a sign of the fact that there is something about quantum phase transitions. Okay? So what we really must have in mind is some normalized metric tensor that scales in the right way. Okay? In which the normal n scaling is taken in account in this way.
First of all, what is n here? Is it n or?
No, I said it. It's this.
And is lambda 0 is actually the variable lambda here, and lambda 1 is variable gamma?
Yeah, so my notation is this. Okay. Okay, lambda 1 and 2 are lambda and gamma. So you see that so now you have to interpret this guy in the large n limit. Okay? So we take care of the n by defining the normalized one. And now you see that for gamma equal 1 and gamma equal 0, this thing diverges. So we recover from the divergence of the distance, of the statistical distance, you know, in differential geometric way, we recover exactly the same phase diagram. So when we apply our new definition, like the critical points are when our distances blow up, then we recover the same phase diagram that we had before. So this works. It's as good definition of phase transitions as before. However, we believe that it's better because it also works when you can have gapless excitations without phase transitions. Okay, so in the cases when there are some cases in which you have a disorder, so your Hamiltonian is the couplings of your Hamiltonian depend on I, depend on the spin in a random way, then typically you don't have quantum phase transitions, but you can still have some gapless excitations. So this is taken in account from the fact that there is a numerator in our G mu nu that is there, you know, that tells us how by changing the Hamiltonian in the mu direction, we can tunnel to the excited eigenstates. Okay, I need to. So of course we can compute all sorts of other things. For instance, we can compute the curvature. Okay, because now this is Riemannian geometry. So let's compute, for instance, the Ricci scalar. So from this you can compute the Riemann tensor, the real Riemann tensor, then the Ricci scalar in this way. So if you compute it, you get two results for depending on lambda. For lambda smaller than 1, we get minus 16 over n, 1 plus gamma over gamma. And for lambda greater than 1, we get 16 over n, lambda plus lambda squared plus gamma squared minus 1 over lambda squared plus gamma squared minus 1. So, and if you see, if you compute the limits for lambda going to 1 from left and right, you will see that you get different results from these two expressions, which means that at lambda equal 1, this quantity is discontinuous. So the curvature is discontinuous. Yeah?
So we get this singular behavior in G mu.
Yeah.
And we go to lambda equals 1. But, so this happens in GR as well, and then you have like a coordinate.
Yeah, here, you see?
Yes.
So when gamma is equal to 0,
there is 1 over gamma.
Yeah. But in GR, we get like this degenerate metric, then that doesn't necessarily imply something physical. So in this sense, is it better to look at the R rather than the G? Or is this?
sorry?
When in general relativity, this G mu nu becomes singular, that doesn't necessarily mean something physical is happening there. It can also be like a coordinate singularity. Is this still the case with like this stuff, or is this like no, these lambdas actually represent like physical things? So when we have this divergence, that actually implies.
So what is that is diverging? What is diverging is the distance between two ground states. So we know that the distance between two ground states has to diverge anyway in the thermodynamic limit just because you have more degrees of freedom. This is the orthogonality catastrophe. So it has an extensive divergence. But at the critical point, the divergence is super extensive. So if you normalize it, basically, if you take, if you divide by n, you have a fixed distance, but in the thermodynamic limit, it still diverges. So it means that two nearby states are much more different than away from that value of lambda or gamma, which is the definition of critical point. It's our new definition of critical point, is when states qualitatively become very different. So we gave a quantitative behavior in terms of this scale.
How do we compute the Ritchie-Scott scalar here? Like, do we consider G, like capital G mu nu as a metric and calculate the crystal symbol?
Yeah. You do you take all the derivatives and you first compute this guy, and then you raise the indices in the right way, and you compute this, and you contract it a few times. So yeah, in the usual way, because this is now just differential geometry.
So we have two different definitions, which is something that seems much easier to calculate and something seems much more difficult to calculate.
Yeah.
And what is the I mean, it obviously provides other points of view, but is there any practical advantage of knowing the R?
Yeah, so for the R, I really don't know. But the interesting object for me is this one. So the reason is that before we first use this criterion of the gapless excitations, however, as I said, there are systems that do not have critical behavior and have gapless excitations. That the so-called mobility gap, like an effective gap. But if you look in the spectrum, they do not have a gap. So also, let me give you a very trivial example, okay? So very trivial. So this is very stupid, but mathematically it works. So imagine that I have two types of degrees of freedom, okay? So I have my spin systems. I have my spin system. And this could be an Ising model, and I'm away from criticality. And then I couple it with some boson system that has gapless excitations, okay? But there is nothing critical here also, just some continuous band. Well, if I compute, and I don't know that it is like this, okay? then I compute the spectrum of my Hamiltonian. I do find some gapless excitations. However, they play no role. So in reality, there are examples less trivial than this, in which there are some gapless excitations, but they do not capture the physics of the correlation functions between the spins, because this is what you want. What you really observe is not the gap in itself. The gap, usually you don't observe it. What you observe is that correlation functions at a distance are not decaying exponentially. Because of this theorem that we keep saying that if there is a gap, then there is a correlation function associated to it such that correlation functions go in this way. So the point is there could be gapless excitations of some other degrees of freedom that are not involved in this observable sphere. So what is the right gap to compute? So in some sense, so this is the meaning of G mu nu. We don't need only to consider the difference in energy between two states, but also how they are coupled by the Hamiltonian when you change the Hamiltonian. Another application is the following. Imagine that I have, so this is something that we will see. Imagine that we have some, something like this. Okay, so we have, this is some critical point here. Here, there are some states that split. Okay? And plus, there is another level that also here has some gaplessness at the critical point. And imagine that these splittings, so they become zero in the thermodynamic limit, right? So imagine that the red one goes like 1 over n, and the white ones go like e to the minus n. And imagine that you want to go adiabatically from one phase to the other, to prepare your state. So now, how slow you have to go? So your time must be much larger than 1 over your gap square, right? So in the thermodynamic limit, this is the gap that is scaling very fast. So you have to go so slowly in order to, you have to wait an exponential time, which means you cannot go really. It's this, no matter what are the coupling constants, for n that is 10 to the 23, you will not be able to do that, in principle, right?
I'm not able to do what? Like to see the gap?
To go from, to stay in the ground state, I start from the ground state of this Hamiltonian, then I change lambda, and I want to stay here, in the ground state of the new Hamiltonian, because I want to prepare this ground state. However, in order to do that, I must be slow enough that I don't tunnel to the excited states. So how slow? So if the spectrum behaves in this way, and I will show you an application, then it seems that if I just look at the adiabatic theorem, I have to wait for a time that scales exponentially. However, in the example that we will see, these tunnelings are forbidden not because of the gap, even though the gap is very, very small, but because this guy also is exponentially small. So if you want to compute your failure to adiabaticity in terms of your metric tensor, you see that actually the gap that counts is this one. And this is the correct answer, because the adiabatic theorem is a sufficient condition, it's not a necessary condition. It's overshooting. You know that if you go that slow, you will be fine, but that doesn't mean that you need to be that slow. it's basically not considering the denominator very well, the numerator very well, if you only look at the gap. So this happens in topologically ordered systems in which there is a quantum phase transition that is marked by all this stuff, meaning that there is a degeneracy. This degeneracy is very tight in the thermodynamic limit. And plus, there is another state that it gives an avoided level crossing. And it's like a usual quantum phase transition. That is the gap that counts if you want to go from a normally ordered state to a topologically ordered state. So you cannot see that if you don't use a criterion like this.
Okay, probably we should stop.
Huh?
Probably we should stop.
Yeah.